Welcome to ECE 341, lecture number 22, Markov Chains. Now, we've been looking at probability in this class, and two slightly different problems. Suppose A and B are playing a match, like they're playing Hungry Hungry Hippo, something like that. A's got a 70% chance of winning any given game, and the match is over when the first team wins 3 games. What's the chance that A is going to win the match? Well, actually, that's a binomial distribution. I have a coin toss. Probability that A wins is 0.7. I'm going to flip the coin 5 times, and if A has 3 or more heads, A wins the match. And that's binomial distribution. We looked at that before. A slightly different problem is same thing. A and B are playing a match. Match consists of games. A's got a 70% chance of winning any given game, but instead of winning 3 games, A has to win by 3 games. So in the second case, if A wins, then B wins, A wins, then B wins, I'm back where I started. That's an infinite series. That's something we haven't looked at yet. That is a Markov chain. So Markov chains handle things like this. You have to win by 2, or win by 3. Now the classic example of a Markov chain is people playing hot potato. Suppose I have 3 people tossing a ball around. If A has the ball, A has a 50% chance of keeping the ball, 20% chance A will pass it to B, 30% it'll pass it to C. If B has the ball, 60% of the time B keeps it, 30% passes it to A, 10% to C. If C has the ball, C either passes it to B or A. Each toss, each K, the player makes a decision and either keeps it or passes it. Where is the ball going to be after K tosses? Well, this is a Markov chain. The probability that A, B, and C have the ball is a function of where the ball was previously times state transition matrix, A. And these probabilities are basically what defines A. So in this case, when A has the ball, A either keeps it, passes it left, or passes it right. When B has the ball, B either keeps it, passes left, or passes right, and so on for C. Now suppose at t equals 0, A has the ball. What's the probability that B will have the ball after K tosses, or after infinite number tosses? That's the type of problem solved with a Markov chain. So this lecture will cover ways to analyze a Markov chain using 3 different approaches. One is using matrix multiply. A second approach is using eigenvalues and eigenvectors. And the third approach is using z-transforms. So let's start with the first approach. Suppose x represents the probability that A, B, and C have the ball, and I'll organize it in this way. The first entry is probability A has the ball, followed by the probability B has the ball, probability C has the ball. The state transition matrix is how to go from x of k to x of k plus 1. That's this diagram. Now the first column is multiplied by the first column of x. So this is if A has the ball, who has the ball next? 50% chance A keeps the ball, 20% chance A passes to B, 30% chance A passes it to C, and the column adds to 1. The ball will go somewhere. The second column is if B had the ball, where does it go? 60% chance B keeps the ball, 30% chance B passes to A, 10% chance B passes to C. Third column is if C has the ball, C passes it to A 40% of the time, passes it to B 60%, and never keeps it. And kind of note, the columns add to 1. The rows don't really tell you anything. So this is the probability of who has the ball given that A, B, and C has the ball. So that's how you set up the system. In MATLAB, I can say here's my A matrix. Here's my initial condition. A starts with the ball. After 1 toss, the probability that the ball is going to be somewhere is 0.5, 0.2, 0.3. That's going to be A times X. After 2 tosses, it'll be that answer times A. So after 2 tosses, A has the ball 43% of the time, B is at 40%, C has at 17%. Multiply by A again, I have 3 tosses, 4, 5, 6, 7, 8, 9, 10. Keep going. After 100 tosses, this is the probability A, B, and C have the ball. Eventually, in this case, X quits changing, reaches a steady state solution. So this would be the steady state solution. The probability that B winds up with the ball is 44.19%. A has the ball 39% of the time, and C has the ball 16% of the time. That's solving this using matrix multiplication. The steady state solution is, if it exists, I can just raise A to a large power, like 100, and just say what is A to the 100th times x0. And one way to check if that's steady state, try A to the 100th and try A to the 101. Sometimes the ball just keeps on being passed around. It doesn't reach steady state. In that case, if the A of 100 is equal to A of 101, that's your steady state solution. Another way to find the steady state solution is in steady state, x of k plus 1 equals x of k. X of k plus 1 is 8 times x of k. So solve for x such that x equals 8 times x. If I do that, bring this to the right, factor out the x, I have a minus I equals 0. So here's the A matrix, there's the identity matrix. Take the difference, I get this matrix. Find A, B, and C such that this is 0. Now this matrix is not invertible, so you can't solve it that way. But what I could do is assume C equals 1. Then if C equals 1, if I have this guy right here, plus this times C equals 0, bringing that right, that times A and B is minus 0.4.6. And for this matrix, multiply, I get two numbers, so there's A and B. Again, A and B. C was 1, but this isn't a valid probability. The sum isn't 1. Take that vector, divide by its sum, I get the probability. Same answer we got before. In steady state, B has the ball 44.19% of the time. A second way to solve is to use eigenvalues and eigenvectors. What you're trying to do is solve x of k plus 1 equals a times x of k. Give it an initial condition, x of 0 is x0. That's actually an eigenvalue-eigenvector problem. And if you recall, eigenvalues tell you how the system behaves. Eigenvector tells you what behaves that way. In general, the response to the system is some constant times the eigenvector times the eigenvalue to the kth power. So I have 3 by 3 matrix. I have 3 eigenvalues, 3 eigenvectors. X of k is just going to be the sum of the 3 eigenvectors. At k equals 0, anything to the 0 power is 1, so this goes away. I can put this in matrix form, factor out the a1, a2, a3 times the 3 eigenvectors. The initial condition times the inverse of the eigenvector matrix gives you the initial condition. How much is the first eigenvalue, second eigenvalue, third eigenvalue excited? If I have initial condition of 1, 0, 0, take the inverse of the eigenvector matrix times the initial condition, that gives your initial condition. So that's 0.61, 0.54, 0.93. So this is the first eigenvector times this eigenvalue to the k, and this initial condition. Second eigenvalue with this initial condition times this eigenvalue to the k. Third initial condition times this eigenvector times this eigenvalue to the k. That's x of k. That's how you use eigenvalues, eigenvectors. Now I can combine these together. And if I do that, I get x of k is this times 1 to the k plus this times minus 0.15 to the k plus this times 0.25 to the k. As k goes to infinity, these terms go away. And there's my steady state solution. So really, the steady state solution is just the eigenvector associated with the eigenvalue at 1. So a shortcut is, given your state transition matrix, just find the eigenvalues, eigenvectors. In MATLAB, if I return two parameters for eigenvalue, I get the eigenvector matrix, the eigenvalue matrix. This is the eigenvalue that I care about. The eigenvalue at 1 is your steady state solution. This one goes away. Decays is minus 0.15 to the k. This one goes away, 0.25 to the k. So these go away, leaving that as steady state. That's my steady state solution, but that's not a valid probability. All probabilities add to 1. This doesn't. If I scale it so it is 1, I get the steady state solution. That's the second way to find it. A third approach is to use z-transforms. So in this system, I've got the problem x of k plus 1 is this matrix times x of k. Call that A. Call that my initial condition x0. Then x of k is A times x of k minus 1 plus x0 times delta of k. X of k plus 1, do a time shift, is A times x of k plus x0 times delta of k plus 1. So in MATLAB, there's a thing called state space. In state space, I have zx equals ax plus bu, use my input. The output y is some matrix C times x plus D times U. That's the state space form. Here my input is a delta function that's shifted forward in time by 1, so that zx0. So when I put this in state space, I'm going to be off by z. We'll see that again a little bit later. The output tells you which state you're looking at. I'm looking at x2. So there's your cx, and there's also a d times u. This is 0. So I can express this in state space form. I've got your zx is ax plus zx0. Bring a to the left, solve for x. This is my response. Multiply by c, that pulls out state x2. And here is my transfer function from the initial condition to y. So that's what I'm trying to find. This is kind of a pain to find. That's a 3 by 3 matrix in Z. Finding the inverse by hand is painful, but fortunately, MATLAB has a solution. In MATLAB, you can input the system in state space form, inputting the A, B, C, D matrix. Here, A is your state transition matrix. C is which state you want to look at. I'm looking at state 2. B is your initial condition, that's x0, and D is 0. T in this case is 1. Every toss, I want to find out what the answer is. In general, T could be something else. Like if I have a digital filter, sampling rate is 1 millisecond, T would be 0.001. In statistics, T is always 1. Once I get the system into state space form, I can find the transfer function in terms of numerator polynomial, denominator polynomial, or in factored form. That's ZPK. So the way I do that is, here's my A matrix, here's my initial condition, there's my C matrix, I want to look at state 2. Input the system in MATLAB, here's my A matrix, there's my B matrix, that's my initial condition, there's my C matrix, D is 0, T is 1. Given that, find the transfer function, or find in terms of zeros and poles, and kind of note, this is the impulse, that's the transfer function from the input, but I really want z times the input, because it's going to be delta of k plus 1, or z times delta of k. So we need to add a z in there. That doesn't show up in MATLAB. You've got to add that manually. That's the transfer function to b. That's b of z. To find b of k, take the inverse z transform. So doing that, here's your b. I multiply by z. Get in the formulation. This is the delta of k plus 1. I want to find delta of k. Well, it tells me delta of k. To get the k plus 1, I need to multiply by z. So to do partial fraction expansion, I'll pull the z outside, do a partial fraction of everything else. To get this term, plug in z equals 1. In this condition, plug in z is 0.25, analyze, get minus 3.1. Plug in z is plus 0.15. I get 2.54. Multiply through by z, take the inverse z transform, and here's u of k. 0.6 times 1 minus 3.1 times 0.25 to the k plus 2.5 times 0.15 to the k. That's the equation for b having the ball after k tosses, found using z transforms. And either way you do it, this is what you get. Probability b has the ball at 0 tosses is 0. At 1 toss, 0.2, 2 tosses, 3 tosses, and there's your steady state solution. Now you can get complex poles. For example, if A, B, and C are tossing the ball around a ring, the ball kind of rotates around. That'll give you a cosine function, showing that it's rotating. When I do this, I'm going to get a complex pole. The inverse Z transform with complex poles is I'm going to have a pole, amplitude of B, angle phi. The amplitude is your b to the k. The angle is phi times k. 2 times A is the overall amplitude, and the phase shift over the minus phi term, that's the phase shift in the output. So illustrate that. Suppose A, B, and C are tossing the ball around. A passes it to B 70% of the time, B passes it to C 80%, C passes to A 90%. Where's the ball going to be? Well, start with the state transition matrix. The first column is if A has the ball, A keeps it 30%, passes it to B 70%. Second column, if B has the ball, B keeps it 20%, passes it to C 80%. If C has the ball, C keeps it 10%, passes it to A 90%. A initially has the ball. I want to know what's the probability B has the ball after K tosses. Solve using Z transforms. So again, what I would do, I'd input the A matrix, x0, my initial condition, a C matrix, I'm looking at state 2. Input that system into MATLAB. Here's your A, x0, C. Your D matrix is 0. T is always 1 in statistics. Now find the transfer function, or zeros, poles, and gains. There's your 0, poles, and gain. That is B of Z if multiplied by Z. Okay, you don't always have to multiply by Z to get the actual transfer function, at least in this class. To find the inverse Z transform, or the equation for B of K, here's your system, multiplied by Z. Pull the Z outside, do partial fraction expansion. I'm going to get complex numbers. Multiply through by Z, and then this is 0.32 times 1 to the K. Double the amplitude, 0.55 times 0.7 to the K. Cosine of K times 106 degrees. So there's your cosine function. It's rotating. Shifted by, turns out this one, plus 126 degrees. That is B of K. And that's what she looks like. And there's the cosine bouncing up and down. That's the ball spinning around the circle, and you can see that in those oscillations. So that's kind of a Markov chain. Markov chain is a way to analyze a problem where you have to win by 2 games, or people are playing hot potato. Winning by 2 games is very different than win 2 games. If you have to win 2 games, that's the binomial distribution. If you have to win by 2 games, that's a Markov chain. And a Markov chain is a discrete probability function where the next state is a function of the current state. X of k plus 1 is A times X of k. And there's a couple ways to analyze systems that are described by Markov chains. I can use matrix multiplication. I can use eigenvalues and eigenvectors. I can use Z-transforms. And so with it, that's lecture number 22 for ECE 341, Markov Chains.